Welcome back to the Tucsen Mastering Scientific Cameras course. And in this part, part 7, Display and Analysis, we're going to be considering some of the factors that are really important when displaying our images on a screen and maybe making qualitative judgments or using the image to explore what's happening in our sample, but also some factors that are really important for the quality of that image. And that image quality then has massive implications for our ability to answer our scientific questions, either through displaying the image on the screen or feeding the image into an analysis pipeline. The first of those aspects is signal-to-noise ratio, and we've mentioned this quite a few times already in this course because it's such a fundamental and important aspect of imaging that we have a good or at least adequate signal-to-noise ratio in our images. And we're going to be exploring exactly what this means and how to calculate it. It's something that there's, in fact, quite a lot of misconceptions and misunderstandings around in imaging, in the imaging world, for how to calculate it and what it represents. Next, we'll be looking more qualitatively at image quality and looking at some of the kind of artifacts that we can sometimes get in camera-based imaging, what kind of effects these can have, and when these might or might not be an issue. Finally, as a subset of that, we'll be having a look at image patterns as represented by these two specifications that we'll sometimes find on camera specification sheets, DSNU and PRNU, and we're going to be defining these in this part. So the first aspects that we're going to have a look at for displaying our image is this question of histogram and scaling. So the question is, does our computer monitor truly show image intensity values? And of course we have a camera of a certain bit depth, as we've explored before. Maybe it's a 12-bit camera with 4,000 different grey levels, and we might have image data with a maximum intensity value from our image of maybe 2,000. So the question is, how do we display this data? As we've talked about before, monitors rescale images to 8-bit, only 256 different brightnesses that a monitor pixel can be. So how do we represent this data? If we have, for example, just set the darkest pixel to 0 and the brightest pixel, the fully white pixel value of our 8-bit monitor, to the brightest possible image value, i.e. 4096 for a 12-bit camera, then that's going to display our image quite dark if our maximum intensity value is only 2000. This would mean that in this case our image is going to be only half as bright as the monitor can show. So this question is, would we want it to just directly show image intensity values? There's also this question of the monitor can't actually, of course, display values above 256 directly as the image comes from the camera. This is different from consumer cameras and our smartphone cameras, which do only produce images with a maximum value of 256. Another thing to note with our consumer cameras and smartphone cameras is that we can sometimes change the exposure or change the intensity, the brightness of the image, and we're free to do that. And if we make an image darker, it's lowering the exposure time, but we do result with a darker image, a blacker image. And that's not necessarily what we want in scientific imaging. Maybe we want to lower the exposure time, reduce our light levels, or work with low light images, but still have a bright image come out of it. And that's where histogram and scaling controls come in. Histogram scaling, also called image scaling or LUTs, lookup tables, determines the brightness that the monitor will represent different image intensity values with. Our monitors are only 8-bit. We have 256 different brightness values, from 0 being fully black or turned off to 255 being the maximum intensity white. And of course the question is, how do we represent 8-bit, 12-bit or 16-bit image data? On the right hand side here we have an example of what an image looks like once it's rescaled. As you can see, this image has a maximum intensity value above 255, so we can't just directly display the image values as the brightness of monitor pixels. Our brightest value is around 1993 there, And our darkest value is also not 0, it's around 101 at the bottom of the image. What we wouldn't want to do is just display from 0 up to the bit depth in this camera, because at the very least this must be an 10-bit camera to have 1024 possible grey levels, but it could be any bit depth. So 993 would be very dark if we displayed the full bit depth in most of those cases. But what we've done with this image, as you can hopefully see, is that our darkest pixel, that 101, is set to our black monitor value, our 0 monitor value, and our brightest pixel, 993, is set to fully 255 white monitor brightness. And then we have a linear scale between the two of them. That is our image scaling settings. And we are in software free to choose usually what these image scaling settings will be to match what our image actually contains in terms of its intensity values, and match our intentions and our scientific questions or our experimental procedures. So we can use appropriate scaling settings for the type of imaging that we're doing. Most scientific imaging software does allow this manual control over the image scaling. And most also allows automatic image scaling, where you don't have to worry about it. Sometimes you have adjustable parameters as well for exactly how this is implemented. And the question is, what is right for your application? We'll just have a look at a couple of different examples of what different image scalings can look like. So on the left here we have a fluorescent microscopy image with, in this case, image scaling, where we've brought down the upper bound, which on the previous slide was set to 993 for that brightest pixel. Here we've brought that down to a value below many of the pixels of the image. So it looks overexposed. It's not overexposed, it's just image scaling that's leading to those white pixels. But what we've done here is reduce this upper bound in order to really zero in on what's happening in the lower intensities areas of the image. So we can see very clearly now what's happening in the dark areas of the image, in exchange for not being able to really tell what's happening in the bright areas of the image. There might be many applications where there's something very bright in our image which isn't actually what we're interested in that image, and we want to really zero in and see what's happening in a darker area of the image, or in a particular scale, a particular area of intensities. Below the image we have the histogram, which, if you're not familiar with image histograms, this represents the brightness overall of the pixels of the image. On the x-axis we have the different possible intensity values for pixels, and then on the y-axis we have the number of pixels that contain that intensity value. As you can see, we have a maximum intensity of something in the region of 580. That's the brightest pixel of the image. But then the modal, the intensity value with the most pixels containing that value is something in the region of 220, somewhere around there. The darkest pixel is something around 85 or 90. Looking now at another image scaling setting, here we have what an automatic image scaling might do to this image. And here, we're seeing the whole thing. This is probably what most applications will want to do. We'll see the image quite clearly across all intensity levels. But one thing to note from the histogram is that the image scaling isn't set to the very brightest and very darkest pixel values, displaying truly every single pixel, with none being just set to fully black and being set to fully white. As you can see, our lower bound 92 is slightly above the minimum value, and our upper bound 562 is slightly below the maximum value. This is because there are bound to be many pixels in the image which have really quite high values due to the random variations of noise within the image. And these highest values can fluctuate quite a lot from image to image. Like, for example, in one image, one pixel might have a value of 700, and then in the next image in a sequence it might be 650. You can really expect very large fluctuations in the upper bound, and some fluctuations too in the lower bound of the image. And if our automatic image scaling is just fully adapting to every single pixel and adjusting our image scaling based on every single pixel, including these sort of outlier high and low pixels, our image scaling is going to change an awful lot from image to image. And that can be really quite distracting and not very helpful for judging the intensities of signals. So what's typically done by by camera software is some degree of ignoring a percentage of the brightest and darkest pixels. So for example, that might be you ignore the darkest 0.1% and the brightest 0.1% in choosing what these image scaling values, upper and lower bounds, should be. And that way we have much more stable images in terms of their image scaling settings, and also this can enhance the contrast that we see things with. The final little case study that we'll look at is if we're interested in the very bright areas of the image. Say in this case, there's something about the structures of the bright part of the image that we're really interested in, and we don't really care about what's happening, at least for now, in the darker areas of the image. We can increase the lower bound of the image scaling settings to give us much better contrast in the brighter areas of the image than we would with the middle case, and certainly than with the left-hand case. In many cases, as I've mentioned, the automatic image scaling might be what you need, but it's important to realize that these options are available to us to explore what's going on in our image and hone in our image scaling on exactly what we're interested in our images. So next we're going to look at this really important subject of the signal-to-noise ratio. And one way that we can think about the signal-to-noise ratio is the limiting factor on how small our signals can get and where we can still answer our scientific questions. Because as we've just seen with image scaling, if our image is too dark, then we can simply change our scaling settings to see what's there and reveal what's there. In many cases, if we reduce, say, our exposure time or our illumination intensity, we might not really notice much difference, initially at least, in our image. Maybe our signal-to-noise ratio is really good, and we don't notice much difference because our image scaling will be adjusting automatically, for example, to cope with that change in intensity. So what's the limiting factor here? What's stopping us just turning our light source all the way down until it's really, really, really tiny and saving energy or reducing the effect on our sample or whatever the incentive there might be for doing this? Well, ultimately, signal-to-noise ratio is the limiting factor on how small a signal we can effectively collect. And it's what determines whether our imaging subject has been captured sufficiently or not for our particular imaging application. In these three examples with three different signal-to-noise ratios, we can obviously see that the left-hand image, we're going to be struggling to tell the structures on this beach, which is maybe not the most ideal scientific example, but we can tell that on the left-hand image we're struggling to tell what's going on. But if we were trying to detect, is there a rock on the beach or not, we can still do that with the left-hand image. It entirely depends what our intentions are as to what signal-to-noise ratio we need for that particular scientific question. But in general, images with different signal-to-noise ratios do tend to look fairly similar to each other in terms of their visual noise and sort of image quality. How much signal-to-noise ratio you need depends, of course, on your application, but at a signal-to-noise ratio of around 20, images will start just looking really nice and clean, and noise won't really be visible by eye. For many applications, this might be the only bar that they need to reach, just for things to be looking fairly good and clean and clear and nice. On the other hand, at a signal-to-noise ratio of 1, our signal is now effectively equal to our noise, and data is unusable in almost all circumstances. Anything in between or above is down to your application for what you need. To see that visually here on the left-hand side, we have a nice fluorescence microscopy image with a signal-to-noise ratio of 23. As you can see, this is very clean. We've got a nice clean background, high contrast, and everything's looking pretty good. As our signal to noise ratio lowers, however, our signal is being lost into that noisy background, and we're losing that contrast that we get as a result. So improving signal to noise ratio and moving from right to left along this sequence means either increasing signal or reducing noise. But what's the most important factor in this? What do you need to focus on in your particular imaging to make the most difference? What actual noise sources are playing the biggest role? This is something that we can calculate by calculating our signal to noise ratio and then truly coming to understand what's going on. So, how to calculate the signal to noise ratio? This is in fact something that is often misunderstood in imaging. There are quite a lot of misconceptions for how signal to noise ratio can be calculated. One might be, say we've got this image on the right hand side here, there's a certain peak value, say 644 in grayscale units, and it's surrounded by some background of largely unilluminated pixels. This might be, a fluorescent molecule or a small object or star or whatever it might be that we're interested in examining. One common and unfortunately incorrect way to calculate signal to noise ratio that I've come across people using is taking this maximum value, in this case 644, and saying, okay, that's our signal. Let's divide that by some average of the background values. So looking at the values in this sort of rectangle of background pixels, we can judge that a average value might be something in the region of 140 or 150. We can then say that, if I divide my signal by this sort of noisy background, I get a signal to noise ratio around 4 or 5. This is unfortunately completely incorrect. It's maybe giving you some rough indication of signal to background, but even that is completely off in this particular way of doing it, because all of these pixel values in almost all scientific cameras will have some offset value, for example 100, added to them. So this straight up division is not serving any purpose at all. Another common misconception is thinking that it some way represents signal to noise to subtract background pixel values from peak pixel values. Like say we take our value, 140, whatever it is for the average of this background area, and subtract it from 640, and that gives us a signal of 500, and trying to make conclusions based on that. That's also not correct for calculating a signal to noise ratio or for judging what's happening from a noise perspective in our image. Again, it's not serving any purpose really. A slightly less wrong but still completely wrong approach is to divide our peak pixel value by the standard deviation of our image background. There's no way basically to access the noise characteristics of our camera from the image that we've acquired. It simply doesn't work like that. We need to access those noise characteristics from completely independent measurements, or more likely from the specification sheet of the camera, or from potentially camera manufacturers might include some kind of calibration sheet or certificate of performance with scientific cameras where engineers have independently measured the noise characteristics of cameras, and they might include that sheet with the camera. That will be the most accurate way to judge the noise of a camera. What you can't do is look at an image like this and make a conclusion about the noise in the image based on the background pixel values. For one thing, there might well be collected photons in those pixels, which will of course contribute to a standard deviation measurement, and then we're effectively penalising cameras for being sensitive and capturing photons because we think those photons are noise. There's all sorts of problems that we come across when we attempt to measure signal to noise ratio from a single image. But there are many creative ways to calculate signal to noise ratio, and unfortunately they will probably all be completely wrong. There is basically only one correct way to do it, unfortunately. But at least it's simple enough to understand once you understand it, and it's a fairly easy calculation to do, so we'll do it on the next slide. But there are a few things that we do need to know, as I've mentioned, to calculate this. One absolutely essential part is we need to know the camera gain with the current settings of the camera in grey levels per electron. One thing I didn't touch on when we were exploring these misconceptions is that all of these values are in grayscales, not in any form of objective unit like photoelectrons. As we saw in the gain section of this course, the engineers who designed the camera can fairly arbitrarily set the conversion scale, the gain, but the conversion between photoelectrons and grey levels. If we're trying to say, okay, we've got lots of signal because the number is 644 and that's quite high, we could have another camera mode where the exact same signal might be represented as 6,440. That doesn't mean that there's more signal. It simply means that the same signal is being represented with a different gain. Yet if we try and make signal-to-noise ratio calculations purely based on image values in this way, that's almost certainly going to throw us off. So we need to convert back to objective units of photoelectrons for our intensities. And to do that, we absolutely need to know the camera gain. We also need to know the camera offset, which is the value that the camera outputs at zero incident signal. For many cameras this is 100, but it's important to check for your camera. One way to check this is to cut off all light to the camera, put on a lens cap for example, and take a number of frames, maybe 10 or 100 frames with no photons hitting the camera at all, and measure the average value of all of the pixels of all of those frames. And that will tell you the camera offset, but it might well be specified by the camera manufacturer or set to some nice round obvious number like 100, in which case it's fairly simple. Another thing that we need to know, as I mentioned, is the noise characteristics of the camera. That includes the read noise and the dark current value. If we're using EMCCDs, then this is a more complicated process that we're not going to talk about in this fairly short course. But for CMOS and CCD cameras, all we need to know is the read noise and the dark current value. And we also need to know our peak or chosen signal value. And this is important to mention because one thing that I've slightly glossed over so far is that in fact every pixel of an image has its own signal to noise ratio value. Of course, every different pixel has collected a different amount of signal. That's actually what our image represents, different signals across the pixels. And of course, different signals means different signal-to-noise ratio values. So the question is, when we talk about an image having a certain signal-to-noise ratio, what do we mean? What's useful for us to mean? And typically, we'll calculate this based on the peak value of the signal within an object of interest. And that might not be the brightest point in the entire image, that might be just the part of the image that we're most interested in, or sometimes we might take an average across a small area of the bright signal from our object of interest. What we can't do is take an average signal-to-noise ratio for every pixel of the image, because of course you can probably imagine that if you have a single bright area within a largely dark image, the signal-to-noise ratio in dark pixels is going to be very, very low, maybe even 1 or less. And therefore, the more dark pixels we have, the more that will throw off our average and not represent really what's happening. So what's typically done is we'll take the brightest point or an average of some bright pixels from an object of interest and call that our signal value, our peak or chosen signal value in grey levels or ADUs. So with all of that said, how do we calculate signal to noise ratio? Here's the formula. Our signal to noise ratio is given by our signal divided by our noise. Though two things to note here with this first left-hand side of the equation is that our signal is in photoelectrons, as I'd mentioned. That's very, very important. Our noise then is added up our various noise sources, the three noise sources that we talked about, the photon shot noise, the read noise and the dark current. It's added up as the squares of these values. We square them, add them, and then take the square roots. And that's how noises have to be added together. So on the right hand side of the equation we have the full form of this, and here you'll notice that the signal in electrons occurs twice in the formula. That's because on the top that's simply our signal, but on the bottom that's our photon shot noise term, which, if you recall, photon shot noise's noise contribution is given by the square root of the signal that we've collected as a Poisson statistics noise source. But because we're squaring our terms before they go into this equation, we've squared that square root away, so it's now just the signal once again. So on the bottom we have the square root of the signal plus our read noise squared plus our dark current term. This is given by our dark current specification from the specification sheet in electrons per pixel per second, and where we have the exposure time as t in there as well. And once again, this is a Poisson behaving noise source, as we introduced in that section, where the square root gives us the actual noise contribution, and then we've squared it, so that square root has gone away once again. So this is the one correct way to calculate our signal to noise ratio. As a quick reminder, how do we get the signal in photoelectrons? Well, once we know the gain and the offset, our signal in electrons is given by our signal in grey levels. That was 644 on the previous slide. Subtracting our offset value, for example 100 if it is that for your camera, divided by the gain of your camera in the given setting that you're using in grey levels per electron. So with that, you'll get a number out the other end which represents your signal to noise ratio. We can use this formula to work out which terms are more important. So for example, if you're trying to work out whether your read noise or your dark current is more significant, if we work out this equation in long form, maybe in Excel or a spreadsheet software, we can see the relative size of the read noise squared, or the d times t parts of the equation, to see if read noise or dark current is something that we need to concentrate more on reducing. We can also see the different effects of, for example, changing pixel size, which will change the amount of signal that we can collect. In general, what we can do with this formula is just compare the results and compare the sensitivities of different cameras and different circumstances when getting an objective number out, which will tell us this is how good our image quality is going to be. This is a very powerful formula once we get accustomed to using it. So onto some more qualitative measurements of the quality of images. Signal to noise is not the only influential factor on the quality of our images. There are things like artifacts that we need to take into account. Artifacts and patterns can be present in images, and that can be an issue for the appearance of our images, but also sometimes for analysis routines that can get thrown off by artifacts. Some common artifacts that you might come across in imaging are, first of all, fixed pattern column noise on the left-hand side here. And this is a problem that CMOS cameras can sometimes exhibit, where, as we mentioned in the readout section, CMOS cameras have a different analog to digital converter on every column of the sensor. These analog to digital converters can sometimes, if they're not adequately calibrated, which is quite an intensive process, if they're not adequately calibrated by the camera manufacturer, they can have slight offset variations, this value that the camera exhibits at no signal. And these slight differences in offset can transmit in the form of a pattern on which low light signals will be overlaid. And this can sometimes be problematic and at the very least be unsightly and not nice to look at. We can also have hot pixels, where individual pixels have particularly high dark current or otherwise have higher values than they should, and by their higher values than their neighbours. We can see this on the right hand side image with these little sort of starry night sky like white pinpricks that we have on the image. This can sometimes throw off image scaling and throw off analysis routines, and it just again generally doesn't look very good. In both cases, though, these are problems that can be avoided by camera manufacturers, or indeed they might simply not be issues for the type of imaging that you're doing. One specific measure of image quality that's sometimes offered by camera manufacturers is DSNU and PRNU. And this is one attempted solution to the problem of representing image quality on a specification sheet for a camera with simple numeric values. Unfortunately, it's not particularly effective, but this is one attempt to do it. And one thing to bear in mind is that the DSNU and PRNU, which I'll define in a second, are simple numbers which attempt to tell a story about a far more complicated and multifaceted issue of patterns and artifacts. And they can only go so far. But DSNU is called the dark signal non-uniformity. And this is an attempt to represent that offset variation of fixed pattern column noise, amongst other issues that I talked about on the previous slide. So this is a numerical representation of the variation of pixel offset, and it's calculated by taking an average of tens of thousands of frames with no light hitting the camera. And once we take that average frame, one frame representing the average value of each pixel in that entire stack of images, we take the standard deviation of that frame, and that represents our dark signal non-uniformity. This is typically represented in units of electrons, which allows us to easily compare it to camera read noise, for example, which is also given in electrons and also represents a variation in our pixels. So it makes sense to compare these two. DSNU is often lower than camera read noise, and if it's lower by much, then it's unlikely to be playing a role in our imaging. We're unlikely to see it very much. However, there is one case in which even small DSNU or small variations in offset are likely to stay visible, and that's the example of fixed pattern column noise that we saw on the last slide. As we can see for this image before corrections for pixel offsets are applied, there's quite a lot of vertical striping in the image, there's quite a lot of fixed pattern column noise, but our DSNU is still really low. It's still well below what a read noise value might be of, at least 1 electron. So this low DSNU value isn't really representing the quality of this image, and this is the primary problem with DSNU measurements. PRNU is similar to DSNU in that it's a numerical representation of variation, but this time it's of the gain values of pixels, which can be slightly different for CMOS cameras from pixel to pixel. But it's only a representation at one specific intensity level, which is one of the limitations of PRNU as a measurement. The variation of gain across different intensity levels is called non-linearity. And in general, all non-scientific cameras are highly non-linear. They actually don't respond linearly to light with more signal directly meaning higher outputted values in the case of non-scientific cameras. Scientific cameras are deliberately designed to be as linear as possible, and they are significantly more linear than non-scientific cameras, but there still might be some small variations. And PRNU won't really capture that because it's only choosing one specific intensity level to represent things at. But once again, it's a standard deviation of tens of thousands of images, or I should say of the average image formed from tens of thousands of images, this time at one fixed illumination intensity. And it's typically shown as a percentage of the chosen signal, which is typically chosen as half the camera's full well capacity. So in this case, if we have a look at an image that the PRNU is formed based on, this average image of all these frames, we can see that there's some slight sort of glow in the center of the image, and that our PRNU is around 1.6%. This is maybe going some way to represent that there's a slight issue with this image before correction. We've now added in the images after correction and after calibration for these issues, and as we can see, the DSNU image is now clean of that fixed pattern column noise, And there's some improvement too in the sort of general noisy appearance of the zoomed in area. But as you can see, our DSNU value hasn't actually changed all that much. From 0.3 to 0.2 electrons isn't really a large enough change to represent the quite large change in image quality that we have between these two background images. With PRNU, however, we've now got a value of 0.3%, and our image does look significantly better. So PRNU might be a better representation, but still we're likely to have this same issue of patterns not being truly represented by PRNU. Another factor is that for low light levels, PRNU is not going to be at all significant compared to other noise sources. And for many imaging situations, we're not going to be working with exactly half the cameras full well, and then the PRNU might even be different at higher or lower signals. So it's quite difficult to represent the entire response of a camera with PRNU. So in general, PRNU should be treated with a little bit of skepticism, as should DSNU, and seeing the actual images that the camera produces, especially at low light levels, should be the measure of image quality. All of that to say, though, this is only when image quality at the low end of the spectrum, especially in the case of DSNU, is really, really important. And for many imaging applications, these variations are going to be so small that there's not going to be any visual effect on our image. I'm going to talk about this in a little bit more later. So finally, to have a look at some image patterns and artifacts that DSNU and PRNU don't represent. Neither can represent dynamic artifacts that change from frame to frame, because both of these are acquired through averaging over multiple frames. Also, neither can represent structured noise, which has a disproportionate effect on image quality versus the standard deviation of the image. Pixels that are too similar to each other, as in the case of a structured noise, that's not really going to change the standard deviation all that much. And this is a problem with measuring things in this way and representing an entire image as one single value. On the right here we have an example of a dynamic artifact where we can sometimes get a scrolling pattern of bright or dark rows of the camera. This is quite a common issue that you might come across sometimes. So in summary, in this section we looked at the signal-to-noise ratio. First off, we examined the histogram and scaling settings, and this is important to make sure that your image scaling settings are set appropriately for your imaging application. These might sometimes require manually setting. In low light imaging, it's more important to set them appropriately than in higher light settings. Our signal-to-noise ratio is one of the most important factors in imaging, especially at low light, where it might be the primary barrier to our image quality, and we can improve it either by increasing the signal or by reducing noise. And we can calculate the signal-to-noise ratio. There's only one correct way to do it, and you do need to know some properties of the camera, such as the gain and the offset and those noise characteristics. Next, we had a more qualitative look at image quality, looking at DSNU and PRNU, which are attempts to represent image quality numerically. They can play some role, they can give some indication of what's going on, but what they won't do is tell the whole story. We also looked at image qualitatively with patterns and artifacts, both dynamic and static, both structured and random, and all of these can affect your image in ways not captured by the signal-to-noise ratio. So on to some examples and applications for this section. First of all, exploring what histogram and scaling settings might be appropriate for different situations. One thing to say is that if you're using a high bit depth, i.e. it's more than an 8-bit camera, typically software can handle image scaling for you. If your image values are way above this sort of 256 level, if they're intensity values in the thousands, then it's much less likely that you're going to need to worry about setting your image scaling to particular values or particular settings. If, however, you're working in low light conditions, Sometimes scaling can be really important to manage to give you the best contrast for seeing what's going on. If your maximum signal, just as a rule of thumb, if your maximum signal minus your minimum signal, which is usually the offset value, if that's less than 256, so less than our number of monitor intensity values that we're going to be scaling against, it might be really important to maximize our contrast via setting the appropriate image scaling settings. And this might not always be very well set by automatic image scaling adjustments in software. Sometimes you might have to do this by hand, and you might have a benefit in contrast by setting the image scaling by hand in these low light situations. A good rule of thumb in low light imaging is to set the lower bound to that image offset, which is often 100. This means that at the very least you're not going to be including noisy areas of the histogram where you can sometimes get values below the camera offset due to the presence of noise in the image, which is both plus and minus in its effect on values. We can sometimes get many pixels below the camera offset, but all of that is going to be noise. So if we set the offset, if we set the lower bound of our image scaling to the offset, then we're going to maximize our contrast through that. Sometimes if we're using a fixed histogram scaling, that can help if we're attempting to judge the change in signal from image to image or from different parts of a sample as we move around or over time. It will help us assess relative intensities or intensity changes by eye, because if we have automatic image scaling and the entire image, for example, changes in its intensity, maybe through photo bleaching, through the reduction in fluorescent signal, we might not notice that because the image scaling will simply adapt to the new brightness settings and our monitor will display it with just the same brightness. If we want to avoid this kind of loss of information, we can fix the histogram scaling, and then if the image gets darker or brighter, we'll see it getting darker or brighter. To summarize and give some examples for signal to noise ratio, once again, your signal-to-noise ratio requirements will vary massively depending on the application and depending on the scientific questions you're attempting to answer with your images. Very few applications only require detection with a signal-to-noise ratio of 2 to 3 to 1. In almost all cases, we need a better signal-to-noise ratio than that, but it again depends on what you're doing. Many applications will require simply visually high-quality images, such as in documentation imaging. This is achieved at around a signal-to-noise ratio of around 20, as we saw before, and there's not going to be a huge difference visually between, say, 20 and 22, or even 20 and 40. We might not, by eye, be able to see a huge amount of difference. That said, there are some applications that require incredibly precise intensity change measurements. And here there's effectively no limit to the amount of signal-to-noise ratio improvement that can be beneficial to us. Sometimes signal-to-noise ratios of 100 or more, maybe several hundred, can help measure the tiniest and most precise of intensity changes. What high signal-to-noise ratio allows us to do when comparing two signals is be confident that any change is down to a change in that signal and not simply a change in the manifestation of the noise in that camera. But remember, with all of this sort of numerical examining and really focusing on the details of signal to noise, the fundamental question is, if your image looks good and meets your requirements for your analysis, that's the most important thing. And you don't necessarily always need to worry about such details if your image is good enough. If you're trying to push things further, maybe it can be very beneficial to calculate signal-to-noise ratio, but it might not be beneficial or necessary for every imaging application. As a summary for DSNU, PRNU, and in general patterns in our image, when are these likely to be significant for imaging? The answer is mostly if you're imaging in low light conditions. As a rough rule of thumb, if you have less than 100 photons per pixel at peak, we might have a more significant contribution of patterns and DSNU if these are unmanaged. As we saw the difference between the calibrated and uncalibrated images earlier when we were talking about DSNU, a well-managed scientific camera might have very low contributions from any form of patterns, in which case it might never really be visible. But if they're less managed, then if you're trying to do low light work, they can sometimes become an issue. Similarly, if you're working with very exact intensity measurements, so you really care precisely what the values are at very high light levels, i.e. close to the camera's full well capacity, then PRNU might become a significant factor for you to be aware of and to try and minimize. But in other circumstances than these patterns and issues with image quality might not be visible at all for your imaging conditions. This might simply not be something that you have to worry about at all with your imaging application. It really depends on what you're doing.